So good afternoon everyone. Today we are going to do the experiment Blackbody. So in Blackbody, first of all you have to turn on the circuit and raise the temperature above 35 degrees Celsius. So as soon as the temperature is above 35 degrees Celsius, for example, I am going to consider 41 volt. So as soon as it becomes 41 volt, I will reduce my temperature to 3.4. I reduce much more. At 3.4, I will set it up finely. You have to reduce very finely. It's 3.4. At 3.4, I will start my timer. As the timer started, I will note down for 1 minute, and correspondingly, as you can see here, my voltage is 3.4. I will note down 3. Show me. I will note down 3.4 and corresponding current point. It's in ampere. Make sure. So it's in ampere 0.334. So my voltage and current I have noted. By multiplying it, I will note down my power, whatever it comes. Now for 1 minute, I will wait, and after 1 minute, I will observe the change in the temperature. So as soon as we can see here, 1 minute is completed. My temperature is 41.2. 41.2, that's fine. Now again after 1 minute, as you can see here, again after 1 minute I will note down the temperature, and again after 3 minutes I will note down the temperature. After 3 minutes you have to immediately note down the temperature, and as well as you have to reduce your voltage. And make sure that timer is keep going on. It will not stop anywhere in between. Now as you can see here, it's 2 minutes and the voltage is 41.8. So now in third minute, I have to note down the temperature, as well as also I will reduce the voltage reading to 3 point. I will also increase the voltage reading to 3.4 to 3.8. Now observe carefully. It's almost 3 minutes, and my temperature is 42.3, and I will increase it to 3.8. 42.3, and I have increased to 3.8. Immediately you have to increase. It's really hard. Even if it's 3.8, fine. 42.3 and it's 3.8. Correspondingly, I have to note down current 0.373. 0.373. You will multiply these two and you will get your power. Now again after third minute, after fourth minute, you will note down your temperature reading again here.
So in this experiment, our main objective is to study the Stefan's law using a copper blackbody radiator. So here, as you can see, this is the copper blackbody radiator. So
just give me 1 second.
Okay, I'll note down the reading first.
It's going to be fourth minute. So in fourth minute, we will note down this reading. As you can see, it's 43.4. So 43.4. Now after 5 minutes, this will be note down 5 minutes, 6 minutes, and in the after 6 minutes, again we will change our voltage to 4, and similarly the current here note down, and similarly the power here, and we will keep, and we will note down these things up to 1, 2, 3, 4, 5, up to 4.2 volt. Similarly, 3.4, 3.8, 4.0, and 4.2, up to 4.2 volt. We will note down all the temperature readings, and after we have noted down everything, let me show that here in the experiment. Now I will turn off this. Now you know how to you have to take the readings. After note down, you will multiply these two and you will get your power here in watt. Since these are in volt ampere, you know, don't need to change any like readings from milliampere. You don't need to. Similarly, simply multiply it, you will get your power, and for the calculation you will take this final reading. For example, now power which you have multiplied here, similarly you will take your this reading and paste here in the second table. This is your power. Area, you know, area is given by 2.463 into 10 to the raised to the power 4. We have calculated it from 4 pi r square area, and where r is the diameter is 14 millimeter, I think 14 millimeter. If you will put this here, you will get your area here in this form. You will divide this reading by the area, this which you will get from by putting value 14 millimeter. You will divide this by this area and you will get these readings here in the unit of watt per meter square. Make sure to take your area in the meter. You will get these reading E by A. After that, you will take your final third minute temperature reading here. You will convert them into the Kelvin, and after turning in them in Kelvin, you will this is your T actually. Now you will calculate T raised to the power 4. When you will do T raised to the power 4, it will come into power of 10. You have to take consideration the power of 10, and that's why it becomes 0.984. So after rescaling to 10 raised to the power 10, you will get your these reading by making T raised to the power 4. Now sigma, we all know sigma is equal to power. What is the formula?
Formula is written here. E by A.
Actually, E by A T raised to the power 4, or simply you can say power by T raised to the power 4. So E by A you have calculated from here. E by A you have calculated from here, and T raised to the power 4. Actually this. So E by A divided by T raised to the power 4. When you will divide by T raised to the power 4, similarly you will get, it will come into 10 raised to the power minus 8 factor, and you will get your all coefficient readings. Now the error method, how you will calculate Stefan's constant by using error method. Since we all know that for the calculation in error, we see that there is a standard value from which we consider this what we say, like how far is our reading from the standard value. There should be one standard reading from which every reading will be far. So we need to find that standard reading. So to find that standard reading, we know that if we considering our standard reading is x, so we will calculate our deviation from x. Since error can be negative as well as positive, that's why we are considering a square here. So square here. So we are considering the square of all the deviations from our each reading. Here, this is, as we can see here, we have taken 5 readings. Since these are the 5 readings, we have 5 readings of the temperature here. So we need to find the best value of the temperature for which our Stefan's constant is precise. To find that best precise value of the temperature, we need to calculate the deviation from the standard value. So to calculate standard value, our error should be minimum. So since error can be positive as well as negative, so we have taken a square here. So Sx is equal to, when we will expand our square, it will come in this form, in this form, in this form. So in order to be the deviation to be minimum, our standard value minus this value should be very equal to 0. When it will become 0, it means our readings are very close to the standard value. So this should be the only case it can be minimum, and it will be minimum only when how should I explain to all of you this?
Like this Sx is
wait.
minimum.
Like Sx should be minimum. Why? Because this is the deviation from each reading. Each reading should deviate very less. So in order to less deviation, our whole Sx value should be very as minimum as we can. So in order to make it minimum, only possibility is, since it's a square, we can't make it minimum. Only possibility is a square can be only minimum case it can only be 0. So this value should be 0 in order to have sx to be minimum. So this value is minimum, means x minus 31.0 is equal to 0. So when this is 0, means the x value, standard value which we have taken, should be equal to this. So this standard value we have taken since x was T. So our standard temperature value we have found this. Similarly, by using the same principle, we will calculate the standard value of E by A. We have considered y is equal to E by A. E by A reading we have taken from here. You can see here 46, 52.3, 58.9, 46, 58, 52.3, all the 5 value. The deviation only, we have considered y is the standard value for which we will take the calculate the Stefan's coefficient. So in order to get maximum deviation from the standard value, this value should be minimum, means square, it should be equal to 0. In order to get 0, y should be equal to this value, and that's why we will get E by A in this form. Why we are calculating E by A and T? Because if we know like for which value E by A and T the Stefan's coefficient is precise, then we will be able to precisely calculate the Stefan's constant. For these values, the deviation from each reading is minimum. For these two values, for sy is equal to for y is equal to E by A, for this value of E by A, and for this value of T, deviation is minimum. It means that the Stefan's coefficient will be more accurate in this condition. So in order to calculate sigma E by A T raised to the power 4, since this value is very less deviation from the standard value, this is the standard value. So our E by A, which we have calculated from this method, is 589.55 divided by the temperature value 31.905, this value, and wait. So since E by A, which we have calculated, what it was came out, E by A is equal to 5.68 589.55, 589.55, and T reading, T temperature reading is 31.905. So since E by A divided by T raised to the power 4, so it's T raised to the power 4. When you will calculate it, my friend here calculated this. As you can see here directly, it's 5.68, which is really close. The ideal value is 5.67 into 10 raised to the power minus 8, and it is 5.68. So nearly it is very. So that's how you will calculate everything. Thank you.